Hi everyone. I'm still dealing with my throat issues, so excuse any hesitations or delays as I mute the mic to cough, and forgive any mispronunciations because I've still got a lot of irritation in my throat. It might not sound like it, but it's actually kind of hard to talk. Now, this video will be DCL-708, but it's also going to be uploaded as DCL-421 because antenna efficiency applies to the VNA, but also I wanted to put a version of this in my antenna, feed line, and SWR folder. So there'll be two videos, they're identical. Before we get started, speaking of DCL-401, DCL-400, that entire playlist is all about antennas and SWR and all that kind of stuff. DCL-700 is instructions, tips, and tricks on the nano VNA. I've wanted to talk about antenna efficiency for a while. I didn't know how to get started. And then Mark, N2IRY, sent me a message and said, hey, could you make a video about how to determine an antenna's efficiency using a VNA? He wants to compare how much of a transmitted signal is actually radiated from a given antenna. This is a wonderful question because it helped me figure out how to present the material you're about to see. The short answer, Mark, is no. You cannot measure an antenna's radiation efficiency with a VNA or a watt meter or an SWR bridge. For that, you must use an antenna measurement range with very sophisticated antennas that very accurately measure the field coming off the antenna. But that's not the end of the story because what you brought up has to do with efficiency overall, and that's what I want to talk about. Let me define a couple terms. The IEEE says antenna efficiency relates the maximum directivity of an antenna to its standard directivity. In other words, how tightly does that Yagi or dish antenna focus the antenna beam? But that's not what you're talking about. You are talking about antenna radiation efficiency. This is the ratio of the total power radiated by the antenna compared to the net power the antenna accepted from the feed line. Let's take a look at something. When we talk about antenna efficiency, we've got to talk about something else, and that is antenna pattern. The isotropic radiator is a mathematical invention of physics. It's a model. It's not real. What physicists did is they said, look, if we dumped all of the RF energy from a piece of cable at a certain power level, if we could invent an antenna that would radiate that RF energy equally in all directions, not in a circle, but in a sphere, what would the field strength be at a certain distance? Well, they calculated what a perfectly efficient antenna would do. All right. Now, of course, it's a theory. It isn't real. But it's a powerful theory. Let's look at a dipole. The dipole, this one, is hung vertically. So here's the sky, here's the ground, and here's the horizon along this line. Now, as you can see, the greatest amount of radiation is toward the horizon. If you drew an arc from here to here, it would be much shorter, telling you that the radiation in this direction is much weaker. There is no radiation to speak of up or down. Compare this to the isotropic model. It radiates in all directions. The dipole is actually radiating in a donut pattern. We've sliced the donut, so the dipole, if it's hung vertically, is radiating in all directions, north, south, east, and west, toward the horizon. But what the dipole is really doing, it's not wasting all this energy that the isotropic throws up here and down here, and it throws it, focusing it on the horizon. Now, if you look, the difference between the isotropic radiation field and the dipole radiation field is this much longer. That represents 2.15 dB of gain. So we say that the dipole has 2.15 dB of gain over isotropic. Now, the dipole's not inventing energy. It's just using the energy better by focusing it on the horizon. This might just lead us to a conclusion. Just because an antenna is not 100% efficient, or as efficient as some other antenna, this does not mean it is not the antenna for what you want to do. So you see, antenna efficiency isn't necessarily the number one factor here. So again, the short answer is, can we measure efficiency with the VNA? No. But there's a longer answer that is very important. And Mark, it's wonderful that you asked the question, because this is a discussion that we must have. What about SWR, forward and reflected power, the Smith chart, all those things that the VNA and our other instruments can tell us? What do they tell us? Well, they don't tell us how efficient the antenna is. If we assume the antenna is efficient, we could say that antenna system efficiency is the ratio of power applied at the shack end of the coax to the power radiated by the antenna. Now again, we don't know how efficient the antenna is, but what is an antenna system? Well, it's the feed line, the tuner, the balance, the radials, the counterpoise, the antenna itself. It's the whole thing. Now, what I'm getting at here is we want the system to deliver as much power to the antenna as possible, and we want the antenna to absorb as much power as possible. The efficiency of the antenna we can't change, we can't even measure. We can assume it's pretty high, and it usually is. But what we really can have power over is how well the antenna absorbs the power, or how well we transfer power to the antenna. That is the most important thing going on here. Let me illustrate this with an example from my work. At work, we might have a transmitter. It's not a transceiver. All it does is transmit. It's a paging transmitter or a telemetry transmitter. Notice that I have 100 watts out and 100 watts made it to the antenna. So my feed line must be very short because it has no loss. But the antenna has a problem. It's reflecting 11.11 watts of energy. That's 11.11% reflected power, which is an SWR of 2:1. If you don't understand SWR, watch my DCL-400 series where I talk about how to calculate what SWR really is. All right, so what we have here is we have reflected power we don't want. Also, this transmitter is at a very busy tower site, and there are antennas very close to this one. So there might be a little energy coming down my antenna line back toward my transmitter that came from some of those other transmitters. When those signals and my reflected power and my forward power all mix in my transmitter, I'm going to get intermod mixes, which will generate terrible interference. So I don't want that. So I put an isolator in. This is the coolest invention ever. If you apply power at the input port, it will go around the roundabout and leave at the first exit, which is the output port. The reflected power comes in the output port, goes around the roundabout, and gets dumped into the dummy load. Now, no matter what my SWR is, my transmitter sees a 1:1. It never shuts down or rolls back. And it also never hears all those other signals that might cause intermod mixes. So isolators are very important. Now, first question, is there really 11 watts reflecting from the antenna back to the transmitter? Yes, and you can prove this by measuring the temperature of the dummy load when you key the transmitter. The dummy load will start to heat up. But we just learned something really cool. We now know that our system is delivering 88.89 watts to the antenna. So our system is 88.89% efficient in delivering power to the antenna. Because we don't know the radiation efficiency of the antenna, we don't know our overall efficiency. But we do know that we are doing an 88.89% job of getting the antenna to take power. And again, there's a lot that we don't know. But we can assume the radiation pattern off the antenna is what we want because we did our homework when we bought the antenna. We don't really know how much is radiated, but we do know how good of a job we're doing at getting that antenna to take power. That system is not like your ham station at home. So let's take a look at what goes on at the house, at our ham station. This is my station. You'll notice once again, no coax line loss. In this case, that's actually almost true because my antenna is less than 30 feet outside the building. I'm running RG8X, and at 20 meters, my loss is like a half a dB. So it's just a few percent loss. So we'll just let that go. I'm losing a little energy in the coax, but we're going to ignore it. Have you ever put a second watt meter in? You got to do this sometime. Now in my case, I'm going to feed my 17 meter ground plane on 20 meters. That's going to result in 50% reflected power, which is an SWR of almost 6:1. Pretty bad. Now let's start out with a HF rig set to 100 watts. Let's see how good this system works. Because it looks like we're only going to get 50% of our power to the antenna. Let's take the antenna tuner out, just temporarily. All right, so here's what we have. Got our radio. Its output comes out here. We loop up. We go to the watt meter, which is also an SWR meter. We come back. We loop through the bird watt meter out toward the antenna. Now let's see what we have. I will key the radio. I will calibrate my SWR meter. And it's very high. I'll flip to the power scale. Now look what we have. This watt meter is on the 2000 watt scale. It claims 50 watts is going out. Well, it's not. This is not accurate at low power levels. But this is. If you take a good look at the 250 watt scale, I got about 25 watts going out. My reflected power is about 12.5 watts, which again is half the power. So my SWR is about 5.5 to 1. Well, you see how inefficient the system is. I'm not sending very much power, and what little I'm getting out there, only half is getting absorbed by the antenna. Why is the power so low? Well, we both know why. My HF rig doesn't like high SWR, so it's shutting down. So this obviously doesn't work very well. Let's go back to this system. Let's put the antenna tuner back in line. All right, here we go again. Radio. Its output goes here. It loops, goes to the meter, comes back, goes to this jack you can't see, which goes to the tuner, comes out of the tuner, goes through the watt meter, out to the antenna. So we have built this. Let's see what we have. All right. I'm going to calibrate my meter. My SWR is almost 1:1. And now it shows 100 watts. At the 100 watt level, this meter turns out to be rather accurate, even on the 2000 watt scale. 100 watts is actually just about right. What do we have at the output of the tuner? Okay, that looks like about, this is a 250 watt scale, about 225 watts. Reflected power, 125 watts. Okay, what's going on here? I'm putting 100 watts into the antenna tuner. I'm getting 220 out with 125 reflected. Well, 220 with 125 reflected, that's my 50% reflected power. That makes sense. Where's all the extra power coming from? There is no extra power. We have 100 watts. It comes out, goes through the tuner, comes up here. 50 watts is reflected. I now have 100 with 50. The 50 comes back here. What happens to that 50 watts when it hits the tuner? The tuner is made of reactances, coils and capacitors. It cannot dissipate energy. It reflects all that power back to the antenna. So now I have an additional 50 watts going to the antenna. So now I have 150 forward, but half that is reflected. So now I have 75 watts coming back. The 75 watts is reflected again. Now I have 220 some watts forward total. You see what happens is the same 100 watts bouncing back and forth gets counted or measured every time it goes by the meter. Now these numbers aren't exactly perfectly accurate because I've got a little loss in the coax line, and my meter is accurate to within about 5%. And I would say 5% at the most. It could even be a little more inaccurate than that. The point here is, first of all, the antenna tuner did not amplify my power. And only 100 watts is making it to the antenna. But do you see what's happened? My reflected power coming off the tuner is near zero. That means this 100 watts, as it bounces back and forth, it can't be absorbed here. This is all reactive. Every time it goes to the antenna, half is absorbed, half is reflected. After this happens several times, you end up with virtually all of the power absorbed by the antenna. We have now invented a system that is almost 100% efficient at getting that antenna to take all 100 watts. Now again, if your feed line has a lot of loss, as the RF is going back and forth, you're losing a little energy every time. With my system, with a half a dB in each direction of loss in the coax, I'm probably getting something like, 94 or 95 watts absorbed by the antenna. So we see what happened here. The antenna tuner did not tune the antenna at all. The antenna is doing what it was doing before. It reflects 50% of the power applied. But the antenna tuner tuned the system such that the transmitter sees a good load and all applied power, or most of it, from the transmitter is eventually applied to the antenna. The only loss we're going to have, the only real loss, is in the coax. So you see, asking about antenna radiation efficiency, Mark, is actually a good question. We still don't know the efficiency of the antenna itself, but we just proved there are ways of making the system at least close to 100% efficient in getting that antenna to absorb the power we are providing. So at least we can do that. Now, if this was not enough for you, I have some suggestions. Go watch all of the videos in DCL-400. You'll learn what SWR really is, how to calculate it, why it's there, all that kind of stuff. You'll learn about wavelength, and you'll learn about all kinds of stuff. If that is not enough, buy this book, or buy Reflections 2, or better yet, buy Reflections 3. As far as I know, they are all out of print. Reflections 3 might still be in print. I found Reflections on eBay for $18. I'm going to give you references at the end of this video, but I'm going to make a statement about this book that I really want you to hear, so stand by. Again, don't miss my other series. So for references, the primary one for this video is Reflections by Maxwell. If you want a university level class in physics and electromagnetics, try the textbooks at the bottom. They are all university textbooks. You'll need a little calculus, and it'll take a lot of months for you to get through these books. Here's what I wanted to say. as much as I enjoy the books in white, they're wonderful. The most readable book on antennas, reflections, SWR, things like that, the most readable book I've read in my entire life is Reflections by Maxwell. If you buy any book, buy that one, whether it's Reflections, Reflections 2, or Reflections 3. Buy the book. And once again, I always have to say this, if you get to my main page, click Playlists, and you get this page. If you want to see every video, if you click on this, you're only going to see one video. But if you click View Full Playlist, you'll get a look at every video in the folder. Thank you so much for watching. I hope this was helpful and fun. And please leave comments and suggestions in the comment section down below the video. Also notice that down below the video, above the comment section, I have a link to my playlist where you can see everything on my channel. Thanks again, and see you next time.